Hello everyone. Today we have the honor to have Professor Andreas Krause in our DDLC seminar. Professor Andreas Krause is a professor of computer science at ETH Zurich, where he leads the Learning and Adaptive Systems group. He also serves as academic co-director of the Swiss Data Science Center and chair of the ETH AI Center, and also co-founded the ETH spin-off Lattice Flow. Before that, he was an assistant professor of computer science at Caltech. He received his PhD in computer science from Carnegie Mellon University and his diploma in computer science and mathematics from the Technical University of Munich, Germany. He is a Max Planck Fellow at the Max Planck Institute for Intelligent Systems, ACM Fellow, IEEE Fellow, Ellis Fellow, and a Microsoft Research Faculty Fellow. He received the Rössler Prize, ERC Starting Investigator and ERC Consolidator grants, the German Pattern Recognition Award, an NSF Career Award, as well as the ETH Golden Owl Teaching Award. His research on machine learning and adaptive systems has received numerous awards at several premier conferences and journals, including the ACM Test of Time Award in 2019 and the ICML Test of Time Award 2020. Andreas Krause finally served as program co-chair for ICML 2018 and general co-chair for ICML 2023 and serves as action editor for the Journal of Machine Learning Research. From 2023 to 2024, he served on the United Nations High-Level Advisory Body on AI. He also serves on the steering committee of the Swiss AI initiative that released the open source LLM named Apertus. Professor Krause, welcome.
Yeah, thank you so much for the kind introduction and for having me as part of this seminar series. Let me try to share my slides. I hope you can see them. Does it work?
Yes.
Wonderful. Okay, great. So I'd like to talk about exploration and reinforcement learning. In particular, how can we enable safe and efficient deep reinforcement learning? And of course, this is joint work with a fantastic set of PhD students, postdocs, and senior collaborators that I'll acknowledge as we go along. Now, reinforcement learning, of course, is this pretty general model of learning to make decisions in our environments, right? It models an agent that tries to figure out how it should act to change the state of the world with the hope to derive some reward from it. And of course, the trouble is that the agent doesn't know how the world works, so it faces this exploitation dilemma, needs to experiment with actions to learn about their consequences and use what it learned in order to do better, right? And of course, that paradigm has been around for several decades, been studied intensively in the AI community, also very closely in control theory, of course, in the context of adaptive control, approximate dynamic programming, and the likes. Nevertheless, we've seen some pretty remarkable advances in quite challenging, also high-dimensional domains, early in games, like Go, for example, but also now in complex robotic policies. So it's state-of-the-art robotics locomotion, for example, right? So our colleagues at ETH use RL to teach robots how to go hike in the Alps. Our colleagues at the University of Zurich use RL to have drones fly faster than human pilots. And of course, RL is used extensively these days to post-train large language models, right? To essentially adapt them to human preferences, optimize reasoning tasks, and the like. So it's definitely quite an exciting paradigm. But I think it's fair to say that RL has been most effective in situations where we have very precise simulators of the dynamics of the environment. A perfect example of this is games. We know exactly how the Go board looks once we and our opponent have taken a move. But of course, in a lot of applications of RL in real-world systems, we don't quite have such accurate simulators. And the question is, can we still somehow make use of this powerful hammer, right, of modern RL algorithms, policy gradient techniques to make progress on some of these tasks? And so some of these examples might include questions from, say, precision agriculture to healthcare questions, right, to more general robotics tasks of interacting with humans. And of course, the key challenge is in science, right? The reason we do science is to learn how the world works, right? You don't have a perfect computational model of it. And of course, in these cases, exploration is not just a computational concern, but it's one where we have to be very careful about sample efficiency and of course also about safety of the actions that we take. And so this is what we want to focus on this talk, right? How we can really get closer to this vision of an agent that learns by interacting with the real world, but does so efficiently and safely. And so I'm going to talk about some of the work that we've been doing in the group. And I'd like to start with a paradigm that is somewhat more restricted, somewhat simpler, but will illustrate some of the key ideas that we'll go back to when discussing deep reinforcement learning later in this talk. And this is safe Bayesian optimization. So here's a motivating example. So this is a collaboration that we had with the Paul Scherrer Institute, so that, in particular on tuning the Swissfeld-free electron laser, which you can see on this picture here. So this is a 700-meter long linear accelerator that generates X-ray pulses of extremely short duration, so femtosecond duration, 1/millionth of a billionth of a second. So you can image extremely fast processes, for example, occurring in the context of chemical reactions. The problem is also quite a complicated machine with many literally moving parts, and the performance of this machine depends on environmental conditions like temperature, humidity, needs to be adapted to task-specific requirements, and so on. So you don't just set it up once, you need to constantly adapt it. The problem is, while in principle it's possible to simulate the physics behind it, these simulations are very, very expensive, and it's also very hard to capture these different environmental conditions. That means you really need to experiment with this machine live while it's being used. And so how are we going to do this? Well, so of course you could just think about this laser as a big black box that you want to optimize. You can inject some tuning parameters, configurations of these magnets that shape the beam properties, and then measure some notion of reward, maybe beam intensity or how close you are to application requirements. But at the same time, safety, of course, is important, right? If you're not careful, there can be beam losses that actually physically damage this machine. But of course, there's lots of sensors deployed in the system that allow to monitor how close you are to violating any of these constraints. The trouble is neither the objective nor the constraints are known ahead of time. And so it means you need to really experiment online while optimizing the performance of this machine, making use of what you've learned so far to close the loop. And so you can think about this basically as this problem of optimizing this generally non-convex objective under non-convex constraints, given only kind of noisy feedback while ensuring safety every step along the way, right? Feasibility of all the iterates of that algorithm. And so it should be pretty obvious that in general, this is a hopeless task, right? So without any sort of prior assumptions, there's nothing you can do. So clearly you need at least a safe starting point, right? We can start. And then you need some sort of assumptions about the shape of the objective F and the constraint G. And one way, of course, to encode prior assumptions is the Bayesian paradigm. And that's exactly what's kind of done in the context of Bayesian optimization, where we would endow the objective and the constraint with a Bayesian prior that allows us to acknowledge the epistemic uncertainty we have about those due to the lack of data and use that uncertainty to navigate this exploitation dilemma. And now we'll later on use these kind of Bayesian models in the context of RL as well. So here's an important cartoon picture that we'll come back to later, clarifying the importance of confidence bounds and credible sets. So suppose we've carried out a bunch of experiments already, shown by these pluses here, and constructed kind of our Bayesian posterior with the mode maybe shown mean shown by this black line, as well as kind of credible sets shown in gray. And if kind of the model is well calibrated, we would hope that the true unknown objective, this blue dashed line here, is covered by these credible sets. And if this is really true, if this model is well calibrated, then we can apply this following rationale. We can look at the pessimistic estimate of the optimal value, this green dashed line here, and then rest assured that the optimum fx star must be somewhere above it, so means constrained in this green region of sort of plausibly optimal solutions. So this allows us to restrict the search space, right? Not search everywhere, right? That's sort of where we hope to find the optimum. Okay. And one way to do this is to be optimistic, right? Optimistic exploration in the context of Gaussian processes that leads to the GPU-CP method. But of course, this optimism in the face of uncertainty principle is really at the heart of exploration and bandits and reinforcement learning and the likes. So now the question is kind of, we want to make use of that sort of picture. Can we really get these kind of well-calibrated confidence sets? And that's where quite a lot of machinery now has been developed over the years. So generally what we would want to do is we want to make sure that we can get sort of these certificates that f of x is really contained within our mean plus some multiple times the uncertainty, the standard deviation of our Bayesian model. But of course, we might not know exactly the prior distribution where the true objective has been drawn, right? And so the true environment might very well be outside of the credible sets of this Bayesian model. But it turns out it's possible to kind of calibrate this model to really get frequentist coverage. So the way you have to do this is to basically scale these confidence sets in a way that depends on kind of the mismatch between the true objective f, here measured in terms of the reproducing kernel Hilbert space norm associated with the covariance function of the Gaussian process models, a family of models very widely used in the context of Bayesian optimization, plus some sort of information capacity term that in a way quantifies the effective degrees of freedom of this prior distribution. Okay, so that's sort of one example where you can really assure that even if f is chosen worst case from some function space, as long as kind of regular enough and satisfies this norm bound, you can construct these types of models in an anytime fashion. So this holds for data even collected adaptively, right, in a closed loop fashion, which is really nice, right? Because later on we'll use algorithms that kind of in a closed loop fashion collect data. There's also some work in sort of trying to push the boundary to what extent you can apply this to neural nets and the like. There's other kinds of constructions. So this is by now quite a large literature around this. This is very well understood for GPs. Later on, I'll talk a lot about methods that use, say, Bayesian neural nets and kind of Bayesian deep learning and so on to do uncertainty quantification. There, of course, this becomes more of an empirical challenge on how do you obtain these well-calibrated models. Okay, now, assuming you have access to these types of models, here's how you can use them to do safe exploration. And this, I want to show kind of one of the first algorithms we proposed in this context, because we'll come back to the main algorithmic ideas in the context of RL in the main part of this talk. And so now let's have our rewards, f of theta, and constraints, g of theta. And so what we want to do is we want to find kind of the constrained optimal solution, right? So we want to be above this dashed line, this constraint, right? And this is the optimal value here. Now, of course, we need a starting point. So we assume we have some initial feasible solution, right? So that clearly we need, as well as this well-calibrated probabilistic model. And now one natural way to kind of proceed is to use kind of pessimistic estimates of our constraints to get sort of a conservative inner approximation of this feasible region that just gives us this red set. And so as long as we kind of explore only within this red set and these confidence sets are well calibrated, right, we should not violate the constraints. And now the question is sort of, given that, how should we explore? And one natural thing that we might want to do is to say, be optimistic, right? Or kind of explore plausibly optimistic, optimal solutions within this safe set shown in red here. Right? So it means basically maybe run the UCB algorithm, right? Or pick points that are plausibly optimal. The trouble with this is if you use standard acquisition functions like being optimistic, then you quickly get into situations like this where kind of a plausibly optimal solution is contained in sort of the strict interior of the safe set, and you're going to be stuck. So instead, what you really want to do is you want to have an incentive to kind of push the boundary, right? To also explore points to allow you to infer in a sort of curiosity-driven fashion somehow, right, that additional actions are safe as well. And so in this paper, we introduce a notion of expanders that basically formalize this, right, that plausibly allow us to infer additional actions as being safe. And then sort of you keep exploring those and eventually determine that actually this solution is really feasible and find that optimal solution. Okay, so we'll come back to all of these ideas, how we kind of do this exploration, safety, and expansion in a RL context later on in this talk. And so that's basically the basic algorithm. So under these regularity assumptions that you need for these confidence bounds to be valid, you can also analyze convergence and convergence rates to a natural notion of reachable optimum in this set. And so this also runs quite nicely on various real applications. So this picture in the top right here shows my former PhD students Maria Mutni and our collaborator Nicole Hiller in the operating room of the Swiss free electron razor, running variants of this algorithm to tune a few tens of parameters of this machine live and adapt them in a safe fashion. Comparing against some standards heuristics that are used to tune this machine online. And since then, there's been quite a bunch of other applications in different domains, like tuning high-precision linear drives, these various kind of tuning control parameters, gain parameters for MPC controllers, other variants of kind of applying this to scientific instruments, some medical applications of this as well. So safe Bayesian optimization by now has reached a whole bunch of different applications. I think it's a pretty cool method. The challenge with it, and with Bayesian optimization more broadly, it's typically restricted to somewhat simpler say, tuning type problems, right? So for example, in this case of tuning the free electron laser, there's a few tens of parameters that we would like to adjust online. It's definitely a non-trivial task, but if you think about reinforcement learning, you typically talk about policies that have like hundreds of thousands, millions, tens of millions of parameters, right? Much, much more complex controllers that we would like to control, right? Completely out of reach of standard techniques in Bayesian optimization. And so what I want to talk about for the rest of the main part of this talk is how we can build on ideas from Bayesian optimization, but lift them to reinforcement learning and learning to control. That's the plan. So what's kind of the gist of Bayesian optimization? So the idea is that we want to acknowledge uncertainty about the environment, say the reward functions, maybe the constraints. And then we're going to introduce some sort of surrogate model, right? And particular an acquisition function that allows us to navigate, to use this uncertainty to drive this exploration exploitation dilemma, right? Or maybe be careful, right, with how we explore and so on. And so what's nice about this framework in principle is that latter step at optimizing this acquisition function, there we can spend, and we're happy to spend quite a lot of computation, right? So this is kind of thinking, right? What next action we should carry out versus carrying out the experiment. This is what matters. So we want to be really, really careful. And so the question is, how can we do this for RL in a way that is compatible with the standard toolkit from DeepRL, policy gradient techniques like PPO, SAC, and the likes? So that's what most of the rest of the talk will focus on. And to that, what you're going to do is we'll take this Bayesian optimization, which is sort of a black box method, and try to sort of open up that black box, in particular, kind of kind of directly model the unknown dynamics, right? Which is, of course, very idiomatic in the context of control systems. So here, let's for now think about unknown deterministic systems. These ideas also generalize to unknown stochastic systems as well. But for now, right, to just keep things simple, right? So suppose the next state is just a unknown deterministic function that depends on a current state action pair. So in a one-dimensional cartoon, this sort of looks like this. Here, the x-axis is our state action pair. The y-axis is the next state, right? That we have some uncertainty about. And of course, you can use the same tools to sort of get calibrated confidence sets that I've described before. Now, if this is our state space, we can now think about using these ideas that I've described before to, say, drive exploration. So suppose you want to reach some goal or get some high rewards or something like this. We could forecast the consequences of carrying out a set of actions or a particular policy that we might implement. And reason about plausible rewards you might get along the way, right? In this case, maybe you want to find a policy that optimistically is able to reach the goal. But of course, we don't really know how the real world works, right? So we might get unlucky, right? And sort of end up somewhere else. But the key idea behind kind of optimistic exploration is either you find good solutions or you visit states that you're very uncertain about. And if you do so, right, you'll learn a lot, right? These confidence sets shrink. And next time you can sort of be more aggressive in terms of planning and find a better solution. That's sort of the gist. Okay, and the question now is how can we sort of, okay, so that's basically for optimistic exploration. And now one can do the same thing, right, for safety in some sense, right? Of now, maybe there's some subsets of states that you don't want to visit. How do we make sure that we avoid those, right? And so that's kind of the cartoon picture. And now the rest of the talk is how to kind of turn this into algorithms, right, that are compatible with the DeepRL hammer, right, where we can throw standard policy gradient methods at it. Okay, so what we want to do is we want to go from Bayesian optimization to basically Bayesian model-based RL. So we'll use a probabilistic model, a Bayesian model, for the unknown dynamics. So that means we have some initial data that might be empty, right? With the prior distribution over our functions f. This could be an uninformed prior, could also be a physics-informed prior. We'll talk about some examples later on in the talk. And then sort of proceed through a sequence of experiments or episodes. In each episode, we refine our posterior based on all the data collected so far, right, to get this model about kind of plausible next states for a given state action pair. And then we would use this policy, right, to think, right, to kind of optimize the next policy that we would like to deploy. This happens purely in silico, right? So there's not interaction with the real system. And then we would roll out that policy pi-n to obtain a new data set, add it to our existing data, and repeat. Right? So that's the standard model-based RL loop. Okay? And so now the second step, of course, is the main important one, right? So the first one is standard Bayesian inference. Rolling out is just standard, right, experimentation with the real system. The main interesting one is the second one, right? And this is basically analog to optimizing the acquisition function in Bayesian optimization. And this is where we want to be able to use standard deep RL machinery, right? And we'll just assume kind of we have access to, say, policy gradient techniques that can solve that problem. Okay, so the question is, how can we do this? And now, so basically, how do we update our policy based on the model? Now, first, what is standard RL? So standard RL, of course, we want to optimize some form of long-term expected reward, say discounted, for example. Of course, there's other objectives as well that we might care about, say infinite horizon average rewards and so on. And the trouble is, of course, that we don't know F star. We don't know the true unknown transition kernel in the MDP. Right? That's what we don't want to assume. And standard deep RL methods would essentially kind of repeatedly generate lots of samples from F star, but that would require lots of environment detections. We want to do this entirely in silico, right? Kind of learn a simulator. Now, the kind of simplest thing we could do is we have our data, we fit a model to it, right? Maybe get our whatever posterior mean of the Gaussian process model or fit a neural network to it, and then treat this kind of as the real world, right? Use through a standard RL solver edit to find our next policy. The trouble with this is that these solvers are very good at exploiting model inaccuracies, right? So there's very much overfits to model errors, right? Sort of dynamics hacking sort of that happens, right? So this often leads to quite poor solution. And even if you could find an optimal policy to this problem, there's no incentive to collect new data, right? You would only be optimal with respect to kind of the wrong estimated objective, not the true one that we really care about. Okay. Now, there's quite a lot of work in the literature sort of to deal with these challenges. So the first one, kind of this overfitting to model errors, one quite popular way of doing so that uses probabilistic models is to basically not just optimize to a single point estimate, but kind of optimize on average with respect to all models from our posterior. In practice, that's maybe some sort of sample-based approximation, moment-based approximation, and so on. Methods like PILCO, PETS, and so on revolve around these types of ideas. And that often is much better at kind of avoiding overfitting to model errors, but still has no incentive to explore. And we'll look at kind of effects of that downstream. So now the question is, how do we exploration? Of course, one canonical way to do exploration in RL is the optimism in face of uncertainty principle, right? That's sort of the heart of classical exploration methods in RL for decades. The question is, how can we do this in this much more complex Bayesian model-based RL setup? And there is a generic way of doing so. That's called basically upper confidence RL. So we would optimize our policies in the outer loop. And the inner loop, we would optimize our plausible dynamics models of the long-term reward you would get under these kind of optimistic dynamics. Okay? So the problem is that this is, in the kind of setting we're talking about here, even if we just use Gaussian process models, right, is a highly non-convex constraint set. So it's not just a non-convex optimization, but a very nasty, very difficult kind of constraint set to work with. Okay? And so it's very hard to implement even to just carry out kind of that optimization, even approximately. And now it turns out the key insight is you can relax this objective and reduce it to just a standard approximate dynamic programming problem where you can throw this deep RL solver, but actually on a sequence of different surrogate MDPs. And this is sort of an idea we'll see throughout this talk of kind of reducing planning to kind of modified versions of the original MDP. So here's how this would work. So this is the original intractable objective. So instead, what we're going to do is we just optimize in expectation with respect to just kind of our point estimate, like maybe the mean model. But instead of optimizing the original reward term, what you're going to have is some sort of additional sort of exploration bonus that is just basically the epistemic uncertainty that comes from the dynamics model, right? So in the GP case, essentially, you look at the corresponding state or state action pair. You can do the same thing for state actions. And then essentially just look at how uncertain you are about the plausible next states. That's basically what this term does. And what you can show is that there is a way to tune these parameters lambda m that under the same sort of regularity assumptions described earlier, that you get valid calibrated confidence sets, you really get a valid, tractable, optimistic value function estimate, right? So this is really an upper bound for it. So in this case, basically, this epistemic uncertainty becomes sort of a curiosity bonus, right? Sort of a notion of intrinsic reward. But it's basically just kind of a slightly modified cost function, modified reward function that you would optimize. Otherwise, the problem is in the form where you can really use standard policy gradient techniques to optimize this objective. And under these regularity assumptions I've described before, you can show that that even though this is an upper bound, it's a tight enough upper bound that one can still get sublinear regret for that sequence of policies being rolled out on the true environment. Okay, so that's the idea. And what's really cool about this is that you can basically integrate it with kind of standard pipelines, right? And standard architectures for model-based RL and apply this to really complex high-dimensional controls tasks. So the first ones are some more simple kind of simulated robots from the Mujoko suite. Also, I've probably seen many of those. And in some tasks, exploration doesn't really help so much, right? In other tasks, can make the difference between being able to learn versus not being able to learn. So the right set of plots here shows on some examples of Atari games. So Montezuma Revenge and Venture are sort of classical examples of hard exploration games, where even kind of the dreamer, so that's really a very strong baseline that doesn't explicitly do exploration, gets stuck, for example, for this Venture game, and you won't get stuck if you use this exploration bonus. Okay, so this is really kind of quite strong baselines where essentially this exploration bonus really does make a difference. And maybe a general comment here. So a lot of the benchmarks where RL is often tested on, there's kind of a lot of reward engineering that went into kind of shaping reward functions, such that policy gradient techniques have kind of a natural direction of improvement, right? But oftentimes, even if you just slightly modify them, for example, introduce action penalties or so, right, where essentially standing still, doing nothing becomes a local optimum, like a local attractor, typically without doing any more involved exploration, you quickly get stuck. But using these exploration bonuses, you won't get stuck, right? If you again look at this cost function here, even if the reward function is zero, right? If you've entirely sparse reward tasks, basically, you still have non-zero rewards that come from sort of this epistemic uncertainty term. So there's a natural drive to explore, right? To kind of keep visiting states that you weren't able to visit before. That's sort of why this helps. Okay, so here's a simple demonstration on somewhat stylized robotics task. So the task is basically to just take this RC car and reverse park it at this designated spot. It's not a super complicated control problem, but it's one where if you really want to model it precisely, you have to think about kind of slippage of the tires and so on, right? Aerodynamic effects and these kind of things. And if you fit kind of too simple of a model, basically, right, do SysID with kind of an oversimplified first principle model and just treat this as ground truth and apply RL to that point estimate. So not using feedback control, right, but essentially kind of using a too simple simulator, then indeed there's a sim to real gap, right? And you won't solve that task. So because of the fact that you don't really describe the environment. So instead of use this model-based RL approach with a prior that basically knows nothing about physics, right? It just makes some basic smoothness assumptions. The first couple episodes kind of spiral off in bad directions, but very quickly you kind of learn something about the consequences of your control actions. And after about 15 episodes, the agent learns to turn around. And after about 20 episodes, it is able to solve that task. And if you use to kind of RL learning curves and so on, right? So 20 episodes is really quite little, right? So it saves several orders of magnitude of experiments that you would otherwise have to do on this platform. Okay, now this is sort of knowing nothing about physics. Of course, in practice, why should we kind of learn Newton's laws from scratch? And so this is, of course, where the Bayesian perspective offers very natural avenues of encoding kind of prior knowledge about the domain. And so, now, of course, one thing you could kind of handcraft priors, but an interesting question is, can you sort of learn good priors from data? And here's actually a very nice way of sort of learning good priors from data. And in particular, what one can try to do is one can try to learn good priors from simulators. So in this RC car example, so one common thing that would be done in practice is to, for example, do domain randomization, right? To maybe simulate a range of different behaviors of how this car might look like, and sort of generate a whole bunch of different MDPs that might be plausible. And all what you could try to do is you could try to compile essentially these different environments into a prior that we could then use for this Bayesian model-based RL downstream. So how would this look? So basically, if you can sort of sample these different environments, just trying to fit a single dynamics model that's consistent across all of them won't work because they're inconsistent. But instead, what we can try to do is we can try to sort of match their correlation, right? They match their statistical signature in some sense, right? What does this mean? Well, you basically need to match the marginals, right? So univariate marginals, of course, are just the function responses at this state action pair. You can look at pairs of marginals in the context of, say, a Gaussian process. These would all be Gaussians, but in general, they need not be Gaussians. In general, you might also care about more than two dimensional marginals and the likes. So all we do is we basically generate a whole bunch of different physical systems to generate a lot of kind of pre-training data and just train a big transformer model to essentially try to predict the score of a given set of data points. And all what you can do is you can basically use score matching, right, to kind of train this transform model and treat that as sort of a data-driven prior. That in a way, it kind of incorporates or absorbs, distills, compresses all the information from the simulator into a regularizer that kind of shape learning. And if you do this, then even the first episode goes in sort of the right direction, so you don't spiral out of control. After already 5 episodes, you almost sort of solve the task, and after about 10 episodes, you solve this task here. Okay, so it's both more safe, quite or more reasonable what it does, right? But it also kind of learns much more efficiently. And so here's a kind of quantitative version of this plot. So the first one just basically just shows on held out data. So you collect basically data by driving around that car, have a train set, test set, fit different models and evaluate always in the same holdout set, the standard pipeline. This is the negative log likelihood. This is just doing SysID on a simple first principle model, right? That of course is too simple for the particular task. So you need essentially almost no data to fit all the parameters, but then you don't get better as you collect more data. This is a baseline where you have this kind of uninformed prior that was used in this first video, right? Where you need to learn physics from scratch. And eventually, you might initially do much, much worse, but eventually you can do better, right? By adapting to kind of the things that are not modeled by this first principle model. One natural thing, of course, is kind of gray box modeling, where you would basically use this ID and learn deviations from it. And that helps kind of improve a little bit at the beginning. But basically using the simulation prior that I've described already allows to start at a better starting point and find better solutions. And here's the closed loop experiment. So that's basically kind of the quantitative version of the video that I had shown you before. Okay, so that's basically how one can use ideas from Bayesian optimization to implement, say, efficient exploration, optimistic exploration. But now, right, the premise to talk was kind of safe and efficient exploration. So let's bring safety back to the picture. And now, of course, the question is, what does safety mean? There's different ways of formalizing this. So one way that's done quite commonly in the safe RL literature is to look at constraint NDPs, where we not just have our rewards as usual, but where we would also have constraints. So we might have a separate cost function that, for example, indicates whether we visit unsafe states, and then this cost basically encodes some sort of chance constraints effectively. And now the trouble, of course, again, is that F star is unknown, right? The environment is unknown, right? So we can't just solve that problem, right? Because we don't have access to F star. So instead, we'd like to kind of have an agent that starts with a safe policy and then kind of iteratively improves it, right? So this is what we now want, right? Kind of how do we enable safe exploration? So the two ingredients are, how do we find even an initial feasible policy, right? Kind of a starting point, and how do we then use it as a starting point to improve, right? Without violating any of the constraints, all while using kind of the deep RL hammer. Okay, so that's the plan for basically the most of the rest of the talk. And so then we talk a little bit about one recent idea at a paper at NeurIPS last year on how to kind of find sort of zero-shot safety, right? Find an initial safe policy. And so I've mentioned domain randomization a few times. Let me just kind of reiterate. So this is really a very widely used tool in robotics, say. So where essentially you would simulate a range of different environments, varying different environmental constants, different mass constants, different parameters or so, to capture some sort of diversity in behaviors. And then basically optimize on average with respect to some distribution of those parameters. And while the resulting policies tend to be more robust, right? So then a single set of parameters that you would fix. In general, of course, right, this doesn't have any worst case guarantees and can be unsafe. But it turns out, at least under some assumptions, you can turn this with a slight variation into a method that actually is provably safe under some conditions. Okay, and so the key insight is the following lemma. So what you can basically show is that you can get a pessimistic estimate of the true constraint cost function, or the true dynamics F star under some policy pi, by looking at the constraint in simulation, right? So the expected cost in simulation, plus some sort of discrepancy term that basically depends on, in a way, the distribution of environments. It depends on the visitation frequencies under the policy. And here, this is basically the Wasserstein-1 distance between the two transition kernels, as well as Lipschitz constant of the value function, and so on, right? So the details of that's out in the paper, but it's some sort of discrepancy term. It comes from a bisimulation lemma, basically comparing the two MDPs. But this suggests, well, let's use augmented costs, right? Similar to the augmented rewards I showed you earlier, right? You can do similar ideas for the costs. We basically have the standard costs of state action pairs, plus basically this discrepancy term or an upper bound of this discrepancy term. The trouble is computing that in general is difficult, except under very simple circumstances. But under some regularity conditions, again, detailed in the paper, you can upper bound it basically by this notion of epistemic uncertainty that I've described to you earlier. But here, this epistemic uncertainty really comes from domain randomization. So essentially look at the variability across different simulations and look at the sensitivity, essentially, or the next state prediction under these different ensemble members. So that gives sort of a cost penalty. And so here's a little illustration, right? Kind of sort of an anecdotal example on this Unity Go 1 robot that sort of walks around, right? Initially, it's sort of safe, right? And at some point, it sort of starts to fall, right? And what this plot here shows essentially is for some time points, right? 1.2 seconds where everything is fine. And later time points, basically 4.6 and 5.3, basically what happens with this uncertainty term, right? And the last one is close to the terminal state. And you really see these spikes of this uncertainty term, right? This discrepancy, the sensitivity term at these point in time. So it's very kind of a very natural kind of intrinsic modification of the cost function that comes from sort of the variability across these simulations. But what's cool about this is you can just, right, again, just replace your original cost by this modified cost and just sort of standard DeBarrel-Hammer edit. And that actually works quite well. Here's some, so there's a bunch of simulation experiments in the paper. These are really simple real experiments on this RC kind of a race car platform in this Unity Go 1 robot. The most important are kind of the last two bars in each of these plots. So these four plots, the first and the third are the objectives, kind of performance, higher is better. And the second and fourth are the costs, right? Where you want to be below the dotted line to be safe, right? To be feasible. Okay, and so here indeed, if you just do domain randomization of the same ensemble of environments and so on that are sort of somewhat reasonably chosen for these settings, the standard domain randomization is actually unsafe, right? And gives significantly higher costs than this pessimistic variant of domain randomization using the method that I've described on the previous slide. And here's just some qualitative comparison of the corresponding policies. So here's basically the domain randomization policy for the Go 1 robot, and the right-hand side is the one that was obtained from Spider. Of course, that's anecdotal, right? But sort of shows qualitatively what happens. This is not particularly performant, right? But it's quite robust, right? And in a way turns domain randomization, which is sort of a standard tool, into a variant that essentially is almost the same, right? But has these augmented costs and actually leads to kind of safe and much more robust policies. Good. So now how can we use this as a starting point to improve on top of it? And that is, I want to briefly talk about the paper that's going to be presented at ICLR in April later this year. And so here we now assume access to a conservative or pessimistic policy. So basically that is really safe across all state action pairs, across all considered dynamics. And so you can think about using this method I've described to you before as one way of sort of training such a conservative method in simulation. There's a second condition that's somewhat more strong, but that's only required for the regret guarantees and optimality guarantees. And now the question is kind of, if you use this sort of policy prior, right, conservative policy prior, how can you use it to safely improve? Okay, and so here's how one can think about this. So let's go back to our constrained MDPs as we had before. So this is the real constrained MDP under the real environment, right, with F star, which is unknown to us. But of course, now we can apply the same ideas, right, with this Bayesian model-based RL, that we quantify the uncertainty now over F star and use this to obtain optimistic estimates for the rewards, but pessimistic estimates for the costs, right? That's sort of a natural way to do this. This is pretty unwieldy optimization, right? You have this inner optimization for the kind of optimistic policies and kind of this pessimistic costs, but conceptually that's sort of a natural thing to do. And now we can use the same type of relaxation that I've described to you earlier, right, with these intrinsic rewards and costs to turn this into tractable value and cost to go estimates. And if you use this, you can basically use kind of these pessimistic cost to go estimates sort of as a safety filter, right, with this conservative policy that you can fall back in. So here's sort of a cartoon explanation of this. So here, this is basically similar to the sort of this RC car setup that's described. So you want to park this car over here, but you want to avoid hitting some of these tires, right? That's the constraint that's modeled here. The optimal policy would sort of go like this. And so now, based on our current model, the current policy would maybe go in this direction, but based on this cost to go estimate, which is basically the current cost already accumulated, plus a pessimistic cost to go, right? It comes from our pessimistic value estimate. As soon as that exceeds the threshold, they're going to trigger the brake, right? And trigger the safety backup policy. Okay, that's kind of a natural thing to do. And so that, of course, then is highly suboptimal, right? Would sort of go off in this direction. Here's a little video kind of just showing this idea in action. So basically, this is sort of the rollout. And here's a slowdown version of it, where basically you kind of follow this policy. And then you essentially at this point trigger this condition, right? Where basically this cost to go estimate exceeds the constraint. And you sort of fall back to this to the safe policy. And now the question is, of course, is how do you improve on the policy to avoid triggering kind of this backup, triggering the safety filter? And turns out there's kind of a really nice way of doing this. Again, just using a reduction to a standard RL problem. Okay, so what you're going to do is you basically convert this CMDP and kind of the safety filter built in into a unconstrained RL problem that we can solve in silico, purely in simulation. And so the way that this modified MDP is going to go, it basically uses the estimated model to predict what's the next state. And now it will also predict whether it would need to trigger the backup policy. Okay? And the transitions where it would need to trigger the backup policy, instead, it sends the agent, right, the kind of in simulation, right? So in the model to sort of a terminal state where the final reward is just kind of this pessimistic reward that you would get from that state onwards. If instead you trigger a transition that would not violate the constraint, even with this pessimistic cost to go estimate, you just proceed according to the standard CMD. That's sort of the idea. Okay, very, very straightforward. And now what's cool about this is basically you can just essentially treat this as an unconstrained standard deep RL problem, throw standard policy gradient methods at it in order to solve it. Right, so basically, again, use the hammer that I've described. Now there's one more challenge. So this is sort of starting to resemble the safe opt algorithm that I've described to you before. But if you remember, so one thing I had pointed out that just optimizing kind of with respect to a pessimistic safety constraints, but being optimistic for exploration is not enough, right? Sometimes you get stuck in poor solutions. And here's another way to see this. So if this is our starting policy, pi 0, then there is this policy pi star safe, which is basically the optimal policy on the set that we can certify to be safe according to our probabilistic model. Okay, so based on all the data we've seen so far, right? This is kind of the best model that we can certify to be safe. And if we were to just kind of do optimistic exploration under this kind of pessimistic safety constraints, then we would only be able to reach that policy pi star. But of course, what we really want to do is we want to find kind of the best feasible policy, right, according to the constraints in the true underlying MDP. But this will require, right, basically pushing the boundary, right, and expanding, right, sort of exploring in a way intrinsically motivated, right, beyond just improving rewards, but sort of trying to push the boundary that eventually we can serve additional policies as safe. Right, that's kind of these purple expanders I showed you briefly at the safe opt algorithm at the beginning. Okay, it turns out that's a really nice way to do this, and actually yields this very simple kind of unified objective that you would apply to this planning MDP that's described to you before. So essentially, it's just the standard approximate dynamic programming problem where you optimize this modified notion of reward that comes from the safe MDP, right? So this planning MDP that I've described. And you have an exploration bonus, and this exploration bonus on one side comes from optimistic exploration with respect to the rewards, but also comes from this pessimistic expansion that you need to do. And there's a way of sort of combining these things that one can still use in order to get regret bounds, right? To basically convergence to sort of the optimal feasible policy. Assuming that you can basically have a subroutine, right, for solving this problem, right? And that's sort of course, where we would apply the standard policy gradient hammer, which is very hard to analyze in general, right? But empirically often works very well. So assuming we can solve these sub-problems here, we can basically show sublinear regret and slightly worse dependence on this information capacity term, but it's sublinear for smooth enough kernels like the Gaussian kernel, for example, or linear kernels and so on. And you, of course, can show really safety every single step along the way. So here's a bunch of first simulation experiments on different simulated CMDPs of different complexity, including some higher dimensional ones, right? Some simulated simplified humanoid tasks. There's comparisons against Sailor. That's a very nice, fairly recent SafeRL method that uses similar notion of planning MDP, but a somewhat modified variant of it. Doesn't quantify explicitly epistemic uncertainty. And here there's basically another CMDP solver, as well as a standard kind of primal dual methods, right? That sort of aims to find feasible solutions at the end, but can't guarantee safety along the way. And so here, again, the comparisons are in terms of the rewards, which is basically the improvement on top of the baseline policy that they started with, right? The conservative initial guess. And the y-axis is the distance from the constraint in the second row, right? How far away you are from the safety constraint. So in the second one, you want to be above zero, right? To have positive distance to the safety constraint. And here, of course, you want to be as high as possible. And so there, the method I've described to you before, right, on safe online optimism for pessimistic expansion in RL, or super for short, is the only one that's really safe across these different environments, and actually achieves pretty good performance across the board on these tasks. And so here is some demonstrations on this hardware platform that I've described to you before. Here, learning takes a little longer, so I cut out some of the episodes. I think there's 35 in total. I'll just show you some of those. We never moved around these constraints, so it never hit any of these tires. So it was really exhibit safe behavior during learning, at least on the trajectory that we've tried here, and eventually actually learns to solve that task. Right, so the initial kind of feasible policy was not able to solve it, right, but was able to avoid it always. And here it's actually able to learn to solve that task. Good. So how do we do in time? So in principle, I could talk a little bit about using some ideas of SafeRL for language models, but I could also take questions. Any advice?
Please keep going. Yes,
Okay, so I have
please.
a couple more minutes. I'll just give the basic idea of this. I think it's also very interesting directions and interesting applications of SafeRL. So I mentioned, right, RL is now getting very heavily used in the context of post-training large language models. So some are basically based on reinforcement learning from human feedback to basically sort of steer generation to completions that match human preferences. It's also used to optimize verifiable rewards and say math and coding tasks, multiple choice tasks, and so on. Okay, and so the generation is a very simple MDP, right? All you do is you basically append tokens, right? So a deterministic transition model somehow that happens. The key question is sort of where does the reward function come from, of course, right? And so there's a lot of work on sort of different types of rewards that you might learn, maybe you even try to not learn them and so on. But the question is, of course, also about safety, right? So for a lot of these tasks, maybe there's some constraints you want to ensure that the LLM satisfies during generation, right? So for example, you might want to ensure that the LLM doesn't output fraudulent behavior, right? Or doesn't output bad jokes or whatever categories you might have. And so the question is now, given sort of this MDP formalism, right? Can we think about kind of safe generation, right, in the context of steering generation, in the context of large language models? Okay, and so here is some initial work that we've been doing in this direction. So it's a paper at ICML last year that describes this. They basically use ideas from safe inverse RL. So we have a data set basically of safe and unsafe behaviors across different categories, and we use this to learn constraints. It's like RLHF, right? But not just learning rewards, but learning constraints. And then basically using ideas from essentially SafeRL to kind of steer to remain within this feasible set, right? To remain within the safe set. Okay. And so the way we're going to do this is as follows. So this is basically a loss function we optimize. Essentially, it optimizes for both sort of a feature extractor that is just a sparse autoencoder, and then essentially just a set of linear constraints that we would use to characterize the decision boundary, basically, of the safety classifier. And so the data we train in terms of the unsafe examples, the data set called Beaver Tails, is a whole bunch of different categories of quote unquote unsafe behaviors, undesirable behaviors of these language models. And we just pool all of that data together. So we forget in a way about these categories and then basically use train this loss function to kind of learn the constraint function, the corresponding CMDP. And what this picture here basically shows is the corresponding constraints that are discovered by the CMDP formulation. So the rows are the true categories, the columns are the learned facets, right? The learned constraints by the corresponding CMDP. And there's a pretty strong correlation across them, right? So it actually is able to kind of, in an unsupervised fashion, sort of disentangle these different failure modes of how the LLM might exhibit unsafe behaviors, which is interesting to see. There's also nice interpretability results sort of coming from this. And so another question is, of course, now that you have kind of these safety constraints, how can you use them to steer behavior? And so one simple way, of course, is to just say, as soon as you output something unsafe, you just don't do it, right? You just stop. But the alternative is also to kind of steer back into the safe set, right? So essentially using CMDP solver. So we do this here at test time, so it's not actually doing post-training. And so now the question is kind of, if we do this, how much does it cost in terms of performance of these models? And that's what these plots show across a bunch of different open weights models, Llama 2, Mistral 2, and Qwen 2 for these experiments. And here's a bunch of different defenses, basically, that have been proposed in the literature across a range of different attacks that we test. And so the x-axis here always shows kind of the attack success rate, to what extent kind of these adversarial attacks that have been done on the LM succeed. And the y-axis is the drop in performance in terms of MMLU, that's sort of a knowledge test set of benchmarks. And so you want to basically be in the top left corner of this plot here, right? Have small attack success rate and high kind of accuracy. And this polytope method that I've described to you before that sort of learns the CMDP and kind of back projects to it does a pretty good job at kind of navigating this, right? And gives better trade-offs than some of the other defenses that I've proposed. There's some caveats around this, of course. So this is not kind of guarding against adaptive attacks, right? So we're not testing attacks that sort of try to specifically kind of attack this defense method, right? And typically these are much more effective. So these are standard attacks that are kind of used and have been proposed in the literature against which it guards pretty well. Okay, so that's basically what I wanted to talk about. I think safe and efficient RL is a super exciting direction. I think it's very important across a range of different domains. And in my view, uncertainty quantification is a crucially important aspect of that. And so there's questions on how do we get models better at knowing what they don't know is really a big open challenge, right? So especially as we sort of scale up models to more complex settings like language models and kind of modern generative AI systems. And so there's quite a lot of efforts here happening in Switzerland in context of the Swiss AI initiative. So you briefly mentioned Apertus in the beginning. That's sort of a large language model that was released by this initiative where sort of a lot of these questions are being very actively studied. So I'd like to just thank all the collaborators, all the students, right, that did the work presented in this talk and the senior collaborators. And just for the recording, here's some of the references that I talked about in this presentation. So thank you very much.
Thank you very much, Professor, for this very nice talk. We have a couple of questions.
Sure.
The first one is about the exploration bonus,
Yeah.
namely the sigma that depends on ST, on the state.
Yes.
Could you explain more about this term?
So let me go back. So this was on probably somewhere almost here, right? So that's the idea, right? So so this exploration bonus. So what does it do? So this is basically looking at a given state or state action pair. You can do this in principle both, right? You look at the epistemic uncertainty of the learned probabilistic dynamics models. So concretely, in the context of GP dynamics models, Gaussian process dynamics models, this is really the posterior standard deviation effectively, right? Suitably scalarized, right? So at the given state or state action pair where it is being evaluated. And so in the experiments later on, right? So here we use basically different neural network architectures as used in a Dreamer model and so on, right? That are basically doing uncertainty quantification. And there's different heuristic ways of essentially quantifying epistemic uncertainty in the context of Bayesian deep learning. It depends a little bit on the method that in particular is being used. So the case where you can prove things about, right, is in the case of RKHS dynamics and GP models and so on, right? So that's there we understand kind of when models are well calibrated and so on. But the kind of uh, idea translates to more heuristic forms of uncertainty quantification in the context of Bayesian deep learning.
So a quick follow-up on this.
Yeah.
Can it be that the posterior uncertainty be so large that we encourage a lot of exploration that we end up being unsafe?
So this here is not about safety, right? So this is purely about essentially optimistic exploration, right? And so that's sort of why when I talked about essentially, let me see if I can swap more directly. Uh, here, right? So for this method that I've described before, right? This is why we use this planning MDP, basically, right? So we use this fallback policy. And if we are kind of very, very uncertain, right, we just always fall back to this conservative prior, right? But hopefully, at least around the initial state or so, we collect enough data that the uncertainty at least there shrinks enough, right? And then gradually we expand the domain where we are confident enough to be able to deviate from essentially this initial backup policy.
Great, thank you very much. The next question um, is it possible to impose uncertainty on the policy being optimized for? In other words, to identify a policy that has a wide, safe operating space that can maximize rewards even when it is not implemented perfectly by a human actor.
So, okay, I'm not quite sure I fully understand. So one setting we had looked at, and I haven't talked about here, right? But one can do entirely reward-free exploration to basically just kind of try to find, say, the largest subset of the controllable state action space, right? That one can reach with the policy, that sort of unsupervised exploration or kind of active system identification, if you want to call it that. And one can try to do that in a safe fashion, right? Where essentially kind of you learn about the safety constraint, but you try to, in a way, explore as much of the reachable state space as possible. And that is actually kind of emergent behavior, even of this method I've described to you before, if you just set the immediate rewards to 0, right? Because then there's no, right? It needs to figure out where it can get positive reward. If the reward is 0 everywhere, it just has to explore everything, right? So that's anyways what sort of happens this way. But what one can show, and that's some work we've shown in previous work, is you can use this to collect initial training data in a purely sort of unsupervised fashion, fit a single model, and then once you have a given reward function, you can optimize it almost 0 shots, right? And get good performance based on it without further hardware experiments.
Thank you very much. The next question is about the expansion algorithms.
Yeah.
Remember this plot that we had. So he asks, I wonder what happens if the policy support has disjoint supports.
Yes, very good question. So similarly, I mean, this was both in this safe Bayesian optimization. Sorry, not wrong slide. Here, right? So this we kind of this algorithm, right? So we kind of expand, but this, of course, doesn't allow, right, to go beyond. So if there would be sort of a separate, disconnected part of the feasible sets, right, you wouldn't be able to reach it, at least not with kind of standard, say, isotropic kernels that only depend on distances and so on, right? So there are some works around kind of safe Bayesian optimization that kind of build on this idea. There's some very nice work out of Sebastian Trippe's group, for example, right? And algorithms like GoSafeOpt and so on that sort of look at that kind of trying to make use of additional information, right? That visited sort of serendipitously. Um, but in general, this is really a challenge with these types of methods, right? That essentially you kind of only can explore what you can reach somehow, right? So if you want to reach kind of a separate independent component in some sense, right? Connected components, you would need to have a safe starting point at this location. And so, I mean, this is right. So same thing for the what I showed you here, there, right? So exactly, right? So typically, um, so local, of course, is local with respect to generalization of the model, right? So the model will have to be able to predict that something is unsafe. Right? And so in the case, this is most easy to interpret in the context of, say, Gaussian process models with isotropic kernels. They really have this, in a way, qualitative behavior that observations tell you something in the local vicinity, right, based on the distance, right? So that's easiest to understand. They're really kind of, it's a matter of essentially it's really locality somehow, right? Of course, if you use neural nets and much more complex feature spaces, also it's much harder to kind of predict which parts of the state space these models will be able to confidently predict as safe, right? So that's much harder to kind of anticipate what exactly will happen.
So a quick follow-up to this, does it maybe what you're describing have a connection with convex and non-convex sets, like the ones I'm seeing here?
Yeah. So I mean, so yes. So certainly, so you don't need convexity, right? So for this reachability, so this is really even if the safe set is so it's really a matter of connectedness, right? It doesn't have to be convex, right? So, but the point is the failure mode is they really have disconnected components. And so in a way, this local exploration, right, is you have a starting point, right? And then you can sort of go from there. And you can only go from there to what extent the data allows you to infer that you can sort of move in a certain direction, right? So that is kind of, yeah, at least with these types of architectures, I think unavoidable.
So we have one last question about the electron experiments,
Oh,
the
yeah,
beamer.
sure.
He wonders some successive tests may be more feasible than others. For example, decreasing temperature and then re-increasing temperature
Yeah.
takes extra work.
Yes. Great
Have you
question.
considered?
Yeah.
Yeah.
So yes. So the question is basically, so in Bayesian optimization, essentially, the parameters are completely considered independent, right? But here, these are physical devices, right? So essentially, if you change even, right, so some of these affect physical configurations of these magnets, right? And you sort of move things around in space, right? And certainly, if you have a certain parameter and go to another parameter close by, this is cheaper, right? Can be done faster, right? Than sort of going to a different part in parameter space, right? And so indeed, there is quite a bit of work in a kind of Bayesian optimization with movement costs, both by our group and others in the community, that sort of looked at these types of problems, right? Where basically you have sort of switching costs that in a way penalize changes in magnitude between different parameter settings. But of course, you could also really think about now writing this down as a reinforcement learning problem as described, right? And use the machinery that I've described in the second part of the talk, where there's really now an explicit notion of dynamics, right? Where you move around. So much of that motivated also right, the second part of this talk, right? What the focus on around.
Professor Krause, thank you very much for this talk.
Oh, sorry, Professor. I just have
Ah,
one more question if you
Yes,
have
sure.
if you have
Oh,
time.
yeah, happy, sure.
Yeah, just like can you elaborate a bit more like in your first part, the more efficiency, you say like your setting is non-episodic setting. I know like the
Ah.
typically reference they are like doubling trick. So I just want like can you elaborate a bit more how can you get rid of this?
Yeah, so very good question. So right, so kind of the episodic versus non-episodic behavior. So what I focused on here is really kind of the episodic setting, where in a way you reset the agent after each experiment. Okay. Now, of course, what you really would want is kind of truly learning online, right? And you're stuck in a state that you've reached and so on, right? And that um, raises some additional challenges. So we looked at this quite a bit. So in this paper that I've described around optimistic exploration. So this OMBRL work that I've described. So this even works in the non-episodic setting under some additional assumptions, right? So, and these are detailed in a paper or so. So in a way, right? So what can go wrong, right? If it basically, so the MDP needs to be navigable enough, right? You can't get stuck in states that you can't ever get out of, right? So if you have these kind of circumstances, you can't recover, right? And it's not possible to have these types of results, right? So, but kind of in these states where you can recover, basically, one can use similar results to the one I've described here, even without having to reset the agent. And so essentially the way we analyze it is actually with the episodic setting, but with episodes of different lengths, right? And then sort of you need mixing behavior and so on. So, I mean, much of this is sort of discussed in this NeurIPS paper that I've described to you before. But yeah, so absolutely, the non-episodic setting in general is definitely more challenging.
Thank you, Professor.
Sure.
Okay, so I don't think there are any other questions. Thank you very much for this seminar.
Sure. Thanks a lot.